Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 24. In this lecture, we'll discuss the law of refraction. This topic is covered in Chapter 35, our textbook by Surway and Jowett. Recall that when electromagnetic waves encounter the boundary between two media, like air and water, two things could happen. A portion of the incident energy can be reflected, and a portion can be transmitted into the new medium. In our last lecture, we discussed what happens to the reflected ray. In this lecture, we want to discuss what happens to the transmitted ray. Transmitted waves usually change their direction of propagation. This phenomenon is referred to as refraction. We can describe the situation as follows. We have two media, which we're labeling as medium 1 and medium 2. You can imagine that medium 1 on top is air, for example, and medium 2 on the bottom is water, for example. We have an incident ray that comes in at angle theta 1. Theta 1 is the angle of incidence, and note that it is being measured relative to the normal line. You can imagine that the incident ray is a laser beam that is incident on a body of water, for example. Naively, you might assume that the incident ray continues to move along a perfectly straight line when it enters medium 2. However, in most cases, that does not happen. In most cases, the ray bends and changes its direction. This bending or changing of the direction is referred to as refraction. What we're saying is that the angle in the second medium is not equal to the angle in the first medium. In other words, the angle of transmission in most cases is different from the angle of incidence. We'd like to be able to calculate theta 2 in terms of theta 1. The law of refraction allows us to do exactly that. According to the law of refraction, which is also known as Snell's law, N1 sine theta 1 must equal to N2 sine theta 2. N1 is the refractive index of medium 1, and N2 is the refractive index of medium 2. Recall that the refractive index basically tells us how fast electromagnetic waves travel through that medium. A little more precisely, N is defined as C over V. C is the speed of electromagnetic waves in vacuum, and V is the speed of electromagnetic waves in the medium of interest. So the law of refraction allows us to calculate theta 2 given theta 1 and the indices of refraction for medium 1 and medium 2. Note that according to the law of refraction, theta 2 can be greater than or less than theta 1 depending on what N1 and N2 are. If N1 is greater than N2, then theta 1 will have to be less than theta 2 to ensure equality. Conversely, if N1 is less than N2, then theta 1 will have to be greater than theta 2 to ensure equality. We can describe those facts as follows. In going from a fast to slow medium, the beam bends toward the normal. A fast medium is one with a low n, and a slow medium is one with a high n. In going from a fast to slow medium, the beam bends toward the normal. What we mean there is that the beam is bending downwards and getting closer to the normal line. On the other hand, in going from a slow to fast medium, that is, a medium with high n to a medium with low n, the beam bends away from the normal. So the beam bends upwards, getting farther from the normal line. In either case, one can calculate theta 2 precisely using the law of refraction. Ultimately, refraction is the result of the change in the speed of propagation. When the wave speed in medium 1 is different from the wave speed in medium 2, the rays bend and the waves change their direction of propagation. On the other hand, if the speed of the waves in medium 1 is equal to the speed of the waves in medium 2, then the rays simply propagate along a perfectly straight line. To better understand that fact, let's consider a simple example. We have two media. On top, we have a fast medium, and on the bottom, we have a relatively slow medium. Suppose the wave speed in medium 1 is 1 unit per second, and in medium 2, it's 0.5 units per second. Here, the unit is some unit of distance. It's not really important what it is. We just want to have easy numbers to discuss. To begin with, rather than discussing the rays, let's discuss the wavefronts. So consider the wavefront at one moment in time. These are 4 points on the same wavefront. You can imagine that these points correspond to points on a peak of the waves as they approach the boundary between the two media. A second later, this wavefront will move forward by 1 unit of distance. So this point will move forward by 1 unit, this point will move forward by 1 unit, this point will move forward by 1 unit, and this point will move forward by 1 unit. A second later, this point will again move forward by 1 unit, this point will move forward by 1 unit, this point will move forward by 1 unit, but this point here is now traveling inside the second medium where things happen more slowly. The wave propagates with a speed of 0.5 units per second in the second medium, so this point moves forward only half a unit. A second later, this point moves forward by 1 unit, this point moves forward by 1 unit, but these 2 points will move forward by only half a unit. And a second later, this point will move forward by 1 unit, but these 3 points will each move forward by only half a unit because those 3 are in the second medium, therefore traveling faster. From here on, the wavefront will simply move forward by half a unit each second. Now, we've been talking about the wavefronts, and you can already see how the wavefront has changed its direction of propagation. To see that better, you can consider the rays. The rays in the first medium will look like these yellow lines here. Note that the rays are perpendicular to the wavefronts. In the second medium, the rays will look like this. In the second medium, the rays are perpendicular to the wavefronts in the second medium. As you can see, the rays have clearly changed their directions. So let's do a practice problem with what we've learned so far. A laser beam with a vacuum wavelength of 632.8 nanometers is incident from vacuum onto a block of lucite as shown. Lucite is basically transparent plastic. It's sometimes described as acrylic glass. The angles of incidence and refraction are measured to be 60 and 35 degrees respectively. Based on this information, calculate the speed, frequency, and wavelength of the laser beam inside lucite. So the situation is shown here. We have a rectangular block of lucite, and we have an incident beam which we've labeled as beam 1. The angle of incidence would be measured relative to the normal to the surface. So this would be the angle of incidence, which we can call theta 1, and that's given to us as 60 degrees. The angle of transmission or the angle of refraction would be this angle, which we can label as theta 2, and that's also given to us. It is 35 degrees. Based on just this information, calculate the speed, frequency, and the wavelength of the laser beam inside lucite. Now, to begin with, recall a couple of important facts. First of all, for electromagnetic waves, laser beams, and in fact all waves, the wave speed is equal to lambda over t. 1 over t is the frequency, so we can say that the wave speed is equal to wavelength times the frequency. Also, according to the law of refraction, n1 sine theta 1 is equal to n2 sine theta 2. N1 and N2 in this case would be the indices of refraction for vacuum and lucite. Theta 1 and theta 2 would be 60 degrees and 35 degrees. Now we know that electromagnetic waves will change their speed as they enter a second medium, and they will also change their direction of propagation, but the frequency does not change. We can express that by saying that the frequency in lucite is equal to the frequency in vacuum. The frequency does not change because the electromagnetic fields in vacuum force the charged particles in lucite to oscillate with the same frequency. When those charged particles begin to oscillate, they in turn generate electromagnetic waves that have the same frequency. So we say that the source frequency is equal to the frequency of the electromagnetic waves. Therefore, the frequency doesn't change, and calculating the frequency in vacuum is easy. The frequency is simply the speed in vacuum divided by the wavelength in vacuum. We know that the speed in vacuum is approximately 3 times 10 to the 8th meters per second, and the wavelength in vacuum is given to us as 632.8 nanometers. And of course, recall that the prefix nano indicates 10 to the minus 9. So that allows us to calculate the frequency inside lucite to be 474.083 terahertz. And recall that the prefix tera indicates 10 to the 12. Next, we're going to calculate the index of refraction of lucite. Calculating the index of refraction for lucite is relatively easy using Snell's law. Medium 1 is vacuum. The index of refraction for vacuum is 1. Theta 1 is 60 degrees. N2 is unknown, and theta 2 is given to us as 35 degrees. Plugging those numbers, you will find that N2, or N for lucite, is approximately equal to 1.510. Now that we have the index of refraction for lucite, we can easily calculate the speed of electromagnetic waves in lucite. The speed in lucite is going to equal to c divided by n in lucite. Recall that n is defined as c over v, so rearranging that equation, we obtain this equation. We now know what n in lucite is. Plugging in those numbers, we find that the laser beam, or the electromagnetic waves in lucite, travel with a speed of 1.987 times 10 to the 8th meters per second. Finally, we can calculate the wavelength inside lucite. Starting with this equation on top and rearranging it for lambda, we find that lambda in lucite is equal to the speed in lucite divided by the frequency in lucite. We now have both the speed and the frequency. Plugging those numbers in, we find that in lucite, the wavelength is 419.109 nanometers. So as the laser beam enters lucite, its speed decreases and its wavelength also decreases, but its frequency remains the same. Let's do another practice problem with the law of refraction. Consider a ray of light traveling from one medium with index 1.4 to another medium with index 1.1. Calculate the angle of refraction when theta 1, that is the angle of incidence in medium 1, is equal to 45 degrees. So as usual, we have two media. The index in the first medium is 1.4 and the index in the second medium is 1.1. Notice that the indices are different, and therefore the wave speed in the two media will also be different. The waves will travel relatively slow in the first medium and relatively fast in the second medium. Since the speeds are different, we expect that the direction of propagation will also change. In other words, if the incident beam comes in at 45 degrees, it will not continue to propagate along a straight line in the second medium. It will bend. The waves will change their direction of propagation. How much the direction changes depends on the indices. A little more precisely, those numbers are related by Snell's law, or the law of refraction, which tells us n1 sine theta 1 is equal to n2 sine theta 2. Now you can see by looking at these numbers that n1 is greater than n2. Since n1 is greater than n2, theta 1 must be less than theta 2 to ensure equality. Of course, you can actually calculate this number by plugging these numbers into your calculator, and you will find that theta 2 is equal to the arc sine of 1.4 divided by 1.1 times the sine of 45 degrees, which is approximately equal to 64 degrees. So the angle of transmission, or the angle in the second medium in this case, will be greater than the angle of incidence, or the angle in the first medium. Let's get a little more practice. This time, calculate the angle of refraction when the angle of incidence is 55 degrees. You can probably use the same formula. However, this time when you plug these numbers into your calculator, you will probably get a math error. You will get a math error because when you plug in 55 degrees into this formula, you will be asking your calculator to calculate the arcsine of a number that is bigger than 1. As you probably know, the sine function can never be greater than 1, so the arcsine of a number that is greater than 1 is undefined. Physically, what this means is that there is no transmission. In other words, if an incident beam comes in at an angle of 45 degrees, there will be some transmission, but if the angle is 55 degrees, then there will be no transmission. Transmission or refraction, in this case, are simply not possible. What that means is that the entire wave will be reflected. This type of reflection is referred to as total internal reflection. The reflection is internal because the beam stays in the original medium, and it's total, meaning that 100% of the incident beam is reflected and none is transmitted. Let's continue the same practice problem. As before, consider a ray of light traveling from one medium with index 1,4 to another medium with index 1,1. This time, we want to calculate the largest angle of incidence that results in transmission. So as we found in parts A and B, when theta 1 is equal to 45 degrees, there is some transmission, but when theta 2 is equal to 55 degrees, there is no transmission. So somewhere between 45 and 55 degrees, there must be some threshold, some maximum angle, some largest angle of incidence that results in transmission. We want to find that angle. According to Snell's law, the two angles must be related as follows. So index in medium 1 times sine of the angle in medium 1 equals index in medium 2 times sine of the angle in medium 2. We're looking for theta 1, so we can isolate theta 1 and write it as follows. Theta 1 is equal to the arcsine or inverse sine of 1.1 over 1/4 times sine of theta 2. Now note that theta 2 can range from 0 degrees to 90 degrees. The maximum value that theta 2 could possibly have is 90 degrees. If theta 2 is greater than 90 degrees, remember that that angle is measured relative to the normal. If theta 2 is greater than 90 degrees, then we basically have no transmission. We have the entire energy being reflected. So we can now say that theta 2 must be less than or equal to 90 degrees if we want to have some transmission. If theta 2 is less than or equal to 90 degrees, then theta 1 must be less than or equal to arcsine of 1,1 over 1/4 times sine of 90 degrees. In other words, we're substituting 90 degrees for theta 2. Sine of 90 degrees, of course, is 1, and the rest of this you can plug into your calculator and find that theta 1 must be less than or equal to approximately 51.787 degrees in order for there to be transmission. If theta 1 is greater than this angle, then there will be no transmission and we will have total internal reflection. This special angle is known as the critical angle for these two media. So the critical angle is that threshold angle between transmission and no transmission. Since sine of 90 degrees is 1, we can always calculate the critical angle by calculating the arcsine of the index of the second medium divided by the index of the first medium. So the previous practice problem was meant to introduce you to the concept of total internal reflection, which is an important concept with some very interesting technological applications, and therefore we must understand it well. Total internal reflection, or TIR, occurs when 100% of the incident light energy is reflected and 0% is transmitted. This happens when two conditions are met. First of all, the index of refraction of the first medium, the incidence medium, must be greater than the index of refraction of the second medium, the transmission medium. We say that the waves must be propagating from a slow medium to a fast medium, otherwise TIR cannot happen. Furthermore, theta 1 must be greater than or equal to this critical angle. This critical angle is the threshold between transmission and no transmission. For theta 1 less than the critical angle, there will be some transmission. For theta 1 greater than the critical angle, there will be no transmission, hence total internal reflection. We can summarize all of that by this figure here. In this figure, medium 1 is at the bottom and medium 2 is at the top. So this is the reverse of the previous pictures that we've been using. Hopefully you have enough mental flexibility to accommodate this change. Here, the incident beam is starting at the bottom and is propagating towards the boundary between two media. If the angle of incidence is less than the critical angle, then there will be some transmission at angle theta 2. Of course, there will also be some reflection, and the angle of reflection will equal the angle of incidence. If theta 1 is equal to the critical angle, then there will be some reflection, and there will also be some transmission, although the transmitted ray will propagate along the boundary. So it's barely staying in the second medium. The angle of transmission, or the angle of refraction, is 90 degrees in this case. If theta 1 is greater than the critical angle, then 100% of the incident ray is reflected and none is transmitted. This final case is referred to as total internal reflection. And that is the end of this lecture. Thank you for your attention.